Okay. So when we're talking about the properties of solids, so here the essential knowledge. Okay, again, this is stuff that we've been talking about, but I guess they just want you to have a specific section on it. Okay. Many properties of liquids and solids are determined by the strengths and types of intermolecular forces present. Because intermolecular interactions are broken, let's zoom in here. Oh my goodness, my computer is dying. What? It's taking forever. It's so slow. Okay. Many properties of because intermolecular interactions are broken when a substance vaporizes, the vapor, pressure, and boiling point are directly related to the strength of those interactions. Melting points also tend to correlate with interaction strength, but because the interactions are only rearranged in melting, the relations can be more subtle. So when we talk about this, so what kinds of materials have the strongest intermolecular forces? Solids, yes. So that's the state of matter that has the strongest intermolecular force. Well, yeah, what kinds of what kind of compounds? What compounds? Covalent bonds have the strongest intermolecular forces?
Yeah, triple bonds.
Okay, so triple bond, that's intramolecular. Remember, that's intramolecular. So when we're talking about ionic bonds versus covalent bonds, remember the four types of bonding? So ion dipole, right? So when we're talking about these different interactions, so when we think about compounds that have really low boiling points. So dispersion, right? So really low boiling point is going to be something that only has interactions with London dispersion forces. Yeah. Yeah, all molecules experience London dispersion. Or as they called it, what, LDF, right? Yeah, what? I don't know off the top of my head. I'll find it though. I'll find it. It is, yeah, 11. Liquid, solids, and intermolecular forces. It's right around the same place that we've been. We've been reading about intermolecular forces, right? Yeah. Okay, so this will lead to our discussion about gases and the ideal gas law. But let's think about things that have really high boiling points, right? What kinds of interactions have really high boiling points?
Like hydrogen bonds, or what kind of interaction?
Hydrogen bonds. So hydrogen bonds occur in water, right? Does water have an extremely high boiling point?
No, but that's because it's small.
Yeah, that's because it's small. That's true. If they were larger molecules, it would have a higher boiling point. But let's think about like metals, right? Alloys.
The stronger intermolecular forces have higher.
Right. So stronger the intermolecular force, the higher the boiling point. Because we're not talking about melting point. The melting point absolutely is influenced by intermolecular forces. But the intermolecular forces still occur in liquids, right? In order to completely break those bonds, not the bonds, but the interactions between the molecules, you have to add enough energy to break all the intermolecular forces. Then the atoms not the atoms, the molecules. The individual molecules jump away, right? That's what boiling is. Okay?
So ionic ones wouldn't have very low boiling.
Ionic compounds would have a high boiling point. Yeah, absolutely. Because ion dipole, right?
Yeah, because they would jump back to whatever makes them less good.
Right. So salt has a very high boiling point, like an extremely high boiling point. We'd have to get an insane kiln to try and boil. Even the ceramics kiln wouldn't get hot enough to boil salt. You can melt salt. That's different. Melting, again, this is boiling. Right? Because in order to boil, you have to completely break the interactions between the molecules.
What would it smell like
if you smelled if you smelled gaseous sodium chloride? I don't know if you're dead. I mean, it would be really hot. So I think that the only sensation you would have in your nose would be burning. if it has enough energy to literally jump away from the interactions of the ion dipole interaction,
it'll smell like
what it'll smell like it would be burning your olfactory receptors in your nose. Because at that point the molecules have so much energy that they're jumping around like that. I am going to start the video here because this is a little bit, so like if they were jumping around like that, I don't honestly know if they can see me now, but if the interactions were broken, if the intermolecular bonds were broken, then it would have so much energy that by the time it got into your nose, it would really damage the cells in your nose. So I don't know if you'd be able to smell gaseous salt. That's a bummer. Okay, go for it. Made it through the door. Okay. So, yeah, I think that that's pretty straightforward, right? We have an understanding that the interactions are only rearranged in melting, but the relations can be more subtle. So, like in melting, it's just that they move past each other, right? They kind of flow and move. In boiling, they completely break. Okay? So let's look at this one here. 5.B.2. Particulate level representations showing multiple interacting chemical species are a useful means to communicate or understand how intermolecular interactions help to establish macroscopic properties. Holy crap, they use a lot of big words there that don't actually have. I don't think that they need to use these huge words. My nose is really itching. What are they trying to say here? What are they trying to say here? Any ideas? B2.
So it says that you can use a particle representation, like a little model. And it will let you gain an understanding about how the macroscopic or like applying to the whole properties work. So like by looking at a model, you'd be able to tell how a gas would behave.
Right. So really what they're saying, particulate level, really what they're saying is something that looks like this. Again, it's not all that like mind-shattering. This is not anything new, right? This is just an ionic solid, right? But if we look at like something like even this, okay, you're not gonna load for me? Okay, whatever. Like this.
So that's a particular level of representation.
Yeah, it's a particular level of representation. It's showing the particles and how they're interacting with one another. I think that they're using, AP people are silly. Okay? Like, how can we make this sound as complicated and complex as possible?
Maybe
Right?
they'll teach them.
Right.
They have to think about it too.
It's true, but it really is just saying, if you can find a model that shows you how the molecules interact, it can help you to understand how it will be in the real world. That's all that it's saying. Right? So if I have my water bottle here, this is probably aluminum with maybe some zinc, some copper, and maybe a touch of iron, right? So how these molecules are interacting with each other, if I was able to zoom in and see how the molecules are interacting with each other, then that would tell me how this bottle would behave if I heated it up. That's really all that it's saying, right? But a macroscopic meaning like in the real world, things that we can observe with our eyes, okay?
Macro is kind of
Yes, Oliver, macro is subjective, you're right. Because you are both infinitely large and infinitely small at the same time. Right? Compared to a Planck length, you are essentially infinitely large. Not perfectly infinitely large, but and you are truly infinitely small compared to the universe. So yes, macroscopic is subjective. I get it. Okay. All right. Due to strong interactions between ions, ionic solids tend to have low vapor pressures, high melting points, and high boiling points. They tend to be brittle due to the repulsion of like charges caused when one layer slides across another layer. They conduct electricity only when the ions are mobile, as when ionic solid is melted or dissolved in water or another solvent. Okay? What is this telling us? Ben, what is this telling us? Yeah, so ionic solids, remember when we look at an ionic solid, it looks like,
well, why do they have low vapor pressures?
So what is a vapor pressure?
If you vaporize something, how much will it expand?
Right. So why would it have a low vapor pressure?
That's the intermolecular forces. Well, they're more
Because the intermolecular forces are stronger. It doesn't expand as much even when you boil it, because they want to be around each other.
Yeah, that's what
Right.
So
Okay.
when intermolecular forces are stronger, vapor pressure goes up.
No, vapor pressure goes down.
Oh.
So vapor pressure goes down in relation to intermolecular forces.
So those forces even apply when it's gaseous?
Yeah, well, the bonds are broken, but they still interact with each other. Right? So if we look at, like, for instance, if we look at your books, if you turn to so your page, it's right around 500. It talks about vapor pressure, surface tension, viscosity, capillary action. Yeah, vapor pressure. Here we go. It'll talk about how vapor pressure is the it's like the amount that it expands. It's how it fills a space, right? Okay, so ionic compounds have high melting points, high boiling points because of strong interactions between the ions.
Says increasing the temperature increases the number of surface molecules with enough energy to overcome the intermolecular forces, and therefore increases the rate of vaporization.
Right. Okay. Questions on that? This is really straightforward stuff. Okay, so 3.2 is very straightforward.
But they make it not straightforward.
Well, they try and make it sound scary, but it makes a lot of sense, right? If the molecules want to stick together more, they're going to be less likely to melt and less likely to. Yowzer! Oh, the ulnar nerve. So I have this problem where the bones in my forearms are really like bowed out at my elbows. So the space in between the two of them, where your ulnar nerve runs, is very big in my arms. So I hit my funny bone, my ulnar nerve, all the time. A few years ago, I hit my right funny bone on the edge of a pool so hard I couldn't feel this part of my hand for 2 days.
That's not good.
Like that's legitimate nerve damage. Like I could not feel this part of my hand for 2 days. I still can't feel this part of my hand right now. I should wear elbow pads all the time. Dude, why do you have elbow pads? Well, I'm just kidding, you gotta be prepared. You never know when you're gonna find a hill that you gotta shred on your longboard, man,
You could get some like arms.
Yeah, anyway, so I hit my ulnar nerves all the time, and I actually hit my right one yesterday. It's almost every day that I hit my ulnar nerve. It's so frustrating. I'm telling you guys, I couldn't feel portions of my arms for days when I hit that on the side of that pool.
I think this is funny because it isn't at all what actual college classes are like.
What this?
Yeah.
What do you mean it's not at all like what actual content?
Like they don't make it extremely complicated, like way more complicated.
I think that AP has kind of an issue where they want to sound smarter than is necessary, I guess.
If all their tests for results.
Right. Okay, so look at all of this, guys. Do you see all this?
Garbage.
Look at all of this. Like most of the sections only have like 3 or 4 topics to essential knowledge topics. 3.2 has 1, 2, 3, 4, 5, 6, 7. I know, it's unbelievable.
Well, it's a good thing that my study guide summarizes it all.
Yeah, okay.
Yeah.
All right, let's see here. In covalent network solids. So what is a covalent network solid?
They're all connected with one another, like a diamond. Yeah, or every atom is bonded.
Yes. So a covalent network bond, remember, it looks like this. You pull it up here.
It's internal.
Okay. This is what it looks like. right? Covalently bonded together into a three-dimensional network, ergo diamond, or layers of two-dimensional networks, ergo graphite, or graphene. Does anyone know anything about graphene? It's a single layer of carbon, all bonded together in the little hexagons. Yeah, well, buckyballs are a different situation. That's essentially graphene bent in all over itself. Yeah, carbon nanotubes, right. Carbon is the best for this when it talks about non-metals, right? Elemental, diamond, and graphite, which is carbon, right? Both of those are carbon. You can get this in silicon as well. Silicon dioxide and silicon carbide. Silicon dioxide, what is silicon dioxide, everyone? It's rock. All right. Oh, thanks. So silicon dioxide is rock, okay? And generally rock is considered pretty hard, right? Due to the strong covalent interactions, covalent solids have high melting points. Three-dimensional network solids are also rigid and hard because the covalent bond angles are fixed. However, graphite is soft because adjacent layers can slide past each other relatively easily. Okay?
So it's not soft, it's brittle.
No.
It's
Brittle would mean if they slip past through one part.
Yeah, that's what it's saying.
Well, they're not attached to each other like bonds from side to side at all.
Yeah, so single layer, which is a graphite. So graphite is two-dimensional, which is just a single layer. Okay? Yeah, that graphite, yeah, if you make graphene is just a single layer. Graphite is a whole bunch of layers stacked on top of each other. But they do not bond between the layers. They're two-dimensional. So they slide around, so it's soft, just like, so it's not exactly like brittle, it's easily scratched. That's what it is. Just like your pencil lead, your pencil graphite leaves marks on the paper because it's rubbing off. It's not being broken per se, it's just being rubbed on to something else. Whereas when it talks about the ionic solids, think about salt, right? You can break salt because once you move a piece, then they repel each other. So you can break ionic solids because they're brittle. Okay? Because of that interaction. All right, covalent network solids. Don't worry, we'll get to the end of this insane list of properties for solids. We need to cover it. I don't know, it seems kind of intuitive. Once you have an understanding of basic intermolecular forces, it starts to make sense, right? But we do need to cover it. All right, next topic. Molecular solids are composed of distinct individual units of covalently bonded molecules attracted to each other through relatively weak intermolecular forces. Molecular solids generally have a low melting point because of the relatively weak intermolecular forces present between the molecules. They do not conduct electricity because their valence electrons are tightly held within the covalent bonds in the lone pairs of each constituent molecule. Molecular solids are sometimes composed of very large molecules or polymers. What is a molecular solid? Yes.
Solid made out of molecules.
Well, all solids are made out of molecules. Yes, that is true. But distinct individual units of covalently bonded molecules attracted to each other through relatively weak intermolecular forces. So, like ice, kind of. So what I look at here is, for instance, nitrogen or dry ice. Yeah, dry ice is a perfect example. Or liquid nitrogen or solid nitrogen. These solids have really, really low boiling points. Okay? Because they are attracted to each other through weak intermolecular forces. So they have low boiling points. A molecular solid like nitrogen, nitrogens are covalently bonded together, right? Or for instance, molecular oxygen. So when we talk about molecular oxygen, when we talk about molecular solids, it's the same deal. Have you ever heard about solid oxygen? No? Probably, you probably haven't heard of it because it only happens at like 6 kelvins.
So it would happen in space.
Yeah, it would. It would happen in space. Well, not near any stars. It would happen in intergalactic space. Because if you're close to a star, the energy being radiated onto the solid would break those bonds apart. So oxygen in nebula is completely gaseous.
Dude, I was just thinking, you can smell the sulfur compounds in products, right?
Yes.
So that means that they're polar. So that means that they freeze at pretty high temperature. So if we lived in a really cold planet, we couldn't smell products because it would just freeze.
That is true. Well, methane doesn't actually have a smell, right?
Exactly, which you couldn't smell.
Right.
So
But methane has pretty strong interactions between the molecules. It's not really strong, but it's strong enough to where it's actually sulfur compounds will freeze at a lower temperature than methane will.
Wow.
Because of methane has really strong
Is it just smaller than
hydrogen bonds. Methane experiences hydrogen bonds.
Well, yeah, but not intermolecular.
Yeah, it does. The hydrogen bonds are intermolecular. Anyway, we got to move on.
No, that's intermolecular.
No, hydrogen bonds are intermolecular.
Well, yeah, but methane isn't polar.
It's true, it's not.
So then how are the hydrogen bonds? Can you have non-polar hydrogen bonds?
Yeah, well, because the hydrogens are on the outside and the carbons on the inside.
Yeah, but it still has no actual
Oh, you're right.
positive and negative.
No, you're right. You're right. Methane doesn't experience hydrogen bonding. You're right. I'll admit it. All right. We got to move on. Intermolecular forces present in molecules, blah, blah, blah. Okay, all this is saying is when you see like molecular nitrogen or molecular oxygen, it's not going to conduct electricity. It's going to have an insanely low boiling point and melting point. Okay, sometimes composed of very large molecules or polymers. So you can get large polymers, like carbon, for instance, right? Carbon can make these really long polymers that you can end up having a solid, but generally molecular solids have very low boiling points. Okay? Oh, last two. Oh, geez. Metallic solids are very good conductors of electricity and heat due to the presence of valence electrons, free valence electrons. They also tend to be malleable and ductile due to the ease with which metal cores can rearrange their structure. In an interstitial alloy, remember what interstitial means, Jane? You remember what interstitial alloys are? Interstitial. What does that mean? Yeah. So in the interstitial alloy, yes, we know that you know this, Oliver. Remember, the interstitial alloy is an alloy of two metals that have different atomic radii. That one of the atoms, one of the types of atoms fits in between the lattice of the other atoms, right? So if you have if you have an alloy between something like titanium and gold, right? Titanium and gold have very different. No, let's do zinc and titanium, right? Zinc and titanium have very different atomic radii, and so the zinc atoms fit in between the atoms of the titanium. Okay, so that's interstitial. Okay, in interstitial alloy, the atoms tend to make the lattice more rigid, increasing malleability and ductility. Oh, sorry, not increasing, decreasing. Alloys typically retain a sea of mobile electrons and so remain conducting. So let's take that example again of titanium and zinc alloy. Because the titanium has the larger atomic radius and the zinc fits in between them, the zinc actually makes it so that the titanium atoms can't move as freely. It makes it stronger, it makes it less ductile, less malleable. Okay? So interstitial alloys are stronger than replacement alloys. Or is it displacement or replacement? Is it a replacement? Yeah, where they just take the place of the other? Yeah.
How do you actually make an alloy?
You just
Put it in a pot.
yeah,
And then
you go,
back together.
here's a chunk of titanium, here's a chunk of zinc. Melt. Mix them around, let it cool, and when it cools, the atoms will align themselves and they'll fill the spaces.
If you cool it really slow, then it'll have a consistent structure.
Yeah, you have to let it cool like slowly. You can't if you flash cool it, then it'll have very, very different properties because the atoms will not have had the opportunity to align themselves.
Real engineering made a video
Okay. Last topic, okay? Biomolecules or polymers, non-covalent interactions may occur between different molecules or between different regions of the same large biomolecule. The functionality and properties of such molecules depend strongly on the shape of the molecule, which is largely dictated by non-covalent interactions. I don't want to worry about this too much. This is getting into organic chemistry, which we'll get to much later in the year, if we get to it at all. Yeah, really what it's looking at, what it's doing is the functionality and properties. So for instance, proteins, okay? A protein is a type of a polymer that has been folded on itself in a certain way. The function, as it says here, the functionality and properties of such molecules depend strongly on the shape. So proteins are folded and they have interactions between the different folds and layers of the protein. These are huge molecules, gigantic molecules, okay? Things that we will not see on like a test about chemistry. We're talking about thousands of carbons with hundreds of hydrogens and nitrogens. And they're all, yeah, sticking to each other. So I don't want to worry too much about that. Questions about the properties of solids. So you, in your notes, since you've all been taking notes, right? Yeah. We need to understand that, I think it's so funny they have this. It's just telling us that models are helpful. Interactions between ions, ionic solids, don't melt very easily, okay? And when they're liquids, they conduct electricity well. Covalent network solids have extremely high melting points. They are very good at staying together. Molecular solids are much more easily broken apart. Metallic solids have characteristics based on on alloys and so forth and how the atoms are aligned. And then don't worry about the biomolecular polymer part, okay? It's just really, I want you to think about proteins. If it ever talks about like bioproteins or biopolymers, think about how proteins are folded on themselves and they interact in between the layers. Okay? What? So imagine a protein is like, that's where I was going actually. It's, cheap ramen?
Yeah.
When you pull it out of the package and then you see all the squiggles and it's rigid. Imagine that's a protein. Okay, it's got all these different squiggles in it and they're all interacting between themselves. Okay? All right. Yeah, proteins are like folded in or on themselves. Yeah, primary, secondary, tertiary, and quaternary structure. Yeah. AP Bio, this is, again, this is kind of bridging the gap between chemistry and biology. That chemistry leads itself to biology and the interactions between the molecules. Okay? Okay, I'm going to leave it at that.
Tertiary protein.
Tertiary protein structure is how it's folded, I believe. Because primary structure is like the order of the molecules. Secondary is the...
There were like two secondary. There's the
yeah,
two levels of secondary.
it's been a long time since I've taken a AP Bio kind of equivalent course. Okay. That's where I'm going to end it for the recording.